Let's relax a little bit. We have had some severe mathematical videos on these hydrogen energies, and we can go deeper and deeper into some more fancy stuff that uses what is it? Let's give us all a break. The math has been very brutal. So we never even cranked out a number for an energy yet because of all the mathematics. So let me back off on this. I've got another play series in my mind that will relate to the further derivation of some of this stuff that I'm going to present. But let's just get to the answers so we can get on with, what did we want to do? We wanted to talk about helium and approximations of the hydrogen model for helium. And what do we need helium for? Well, we needed helium so we could get into some more complex models that involve more than one electron. And what do we need that for? We needed to get into some more complicated computer models. And what kind of computer models? Computer models that will help us with the iron molybdenum cofactor molecule. And what's that? And why do we need that? Well, that's to help us solve the nitrogenase problem. So all of these things fit together even if we lose sight. So this is going to do a little bit of hand waving about what's happening, but it's going to be good so that we can move forward. Some of this stuff should look familiar to you. Angular time-independent Schrodinger equation where we let x equals cosine theta, and that simplified the angle thing. This isn't exactly what we got before, but it's really along the same lines. Here we have 1 minus x squared, which essentially is sine squared, derivative of big theta with respect to x, plus here's lambda minus m squared over 1 minus x squared. So that's really sine squared if you think about it. Set that equal to 0. Then here's where some hand waving comes from. M is the magnetic quantum number. Lambda is the separation constant. And regular solutions of the associated Legendre polynomials. What's that? Well, if you want to know, look in another playlist that I have to design to get all that stuff. Here's the P, though. We had P in the last video. So here's the M, and here's the newly introduced L, which is the angular momentum L. And L can be 0, 1, and 2, and we'll find out that M can be equal to minus L or plus L. L is just the whole numbers. We're not including the negative numbers. So let's go down here to the radial part of the time-independent Schrodinger equation. And some of this, remember we substituted U, and this is the same substitution, only we're using it with R over A sub 0. A sub 0, that's the radius of the Bohr atom. So the original model where they figured out what the radius had to be for the electron at ground state. Here's all this stuff. May look familiar, may not. If you want to go back to the video where we did some of this stuff, that's fine. If not, who cares? Let's move forward. Let's get on with something real so that we can finally get into something that will help us with the nitrogenase problem. Here's the big R function, and Frobenius ansatz. That's in that other series, so I'm not going to mess with that. And leads to the quantization condition via series termination. We're just going to have to gloss over this for right. So let me go here for hydrogen energy levels. Now we're getting down to something. Termination of the series requires that n sub r, that's the radius part, plus L plus 1 equals n. So n is the principal quantum number. Principal quantum number, if you think about your chemistry class, the principal quantum number is whether you're in level 1, 2, 3, 4, and so on. N sub r is the radial quantum number. That's the same thing, 0, 1, and 2. E sub n is equal to m e to the fourth 2. Here's that h bar squared thing. Here's the potential energy factor, 4 pi permittivity of free space, and n equals a radius number. So that's how this is potential energy. And the m is, what's the m come from? Well, the m came from this m up here. So how do we get anything out of this? Well, the primary energy cranks out to be 13.6 electron volts. So that's a big step here. Then the next energy out is less. We go from 13 to 3, and then we go from 3 to 1.5, and then to 0.85. So all of those equations led to this result. And if you want to see what's in between where we last left off and where we are and where we get to here, I've designed a nice playlist for us, which is going to be ugly to the non-mathematician, but beautiful to the mathematician.